All the circuits that we have studied with op-amps take advantage of the negative feedback in order to adjust the gain. In this lesson, we are going to explore what happens when there is no feedback or there is positive feedback. Let's figure out if we can do something useful with these configurations. If you recall the op-amp formula we use, you'll remember that there is a term that represents the op-amp gain. This gain is very high. In some of the op-amps I use, the manufacturer reports a gain of around 200,000. If we connect a voltage source of 1 volt to the positive terminal and the negative terminal is connected to ground, the difference will be 1 volt. Then it is multiplied by the gain. That means that we should have 200,000 volts, right? Well, that's wrong. We will only get a voltage as large as the power supply. If the op-amp is a rail-to-rail op-amp and has a power supply of plus minus 12 volts, we will get 12 volts as output. If the voltage of the positive pin starts decreasing, as soon as it becomes less than the negative voltage, which in this case is 0 volts, the output will rapidly change to minus 12 volts. We can see this behavior in the following simulation. In blue, we can see the input voltage and in orange the output. This operation is basically a comparison. When the voltage is larger than 0, the output is 12 volts, and when it is less than 0, the output is minus 12 volts. In a real op-amp, there are a few things that we need to consider. If you remember the previous lesson on real op-amps, there is a small offset voltage at the input. That will make the comparison not exact, but maybe good enough for most applications. Additionally, the change from positive to negative voltage at the output is limited by the slew rate. If this is an issue, there exist special op-amps that are enhanced to be used as comparators. Those present less offset and faster slew rate. Additionally, they can be used in cases where we don't want output as large as the power supply. There are some applications in which this comparator can be problematic. The following simulation shows a special case in which an input signal has some kind of noise. We can see that the noise produces bursts of pulses. This is caused by the input signal crossing multiple times the 0 voltage level. In the second plot we can see a close-up. Here we can clearly see the places where the input crosses 0 and that produces the extra jumps in the output signal. As mentioned before, this can be problematic for certain applications, and it would be great if we could have a safety margin to avoid these jumps when the input voltage barely crosses. There is one special type of comparator called with hysteresis. This type of comparators offer exactly the kind of safety margin that we want. The following diagram shows how they work. Let's imagine that we start with a large positive signal, which makes the comparator output the positive VCC. Then the input voltage starts decreasing. At some point, it reaches 0 volts, but the output of the comparator doesn't suddenly change. The input needs to become even lower for the comparator to change. It needs to be less than the voltage minus T in order to change. This voltage is what is called the threshold, and it is what defines the safety margin. After crossing the threshold, the comparator changes. Now, if the voltage starts increasing, it needs to reach a new voltage threshold value before it changes. The new threshold is plus T volts. How does this behavior help us avoid the problem of noise in the input? After the threshold is crossed for the first time, the new threshold value avoids the comparator changing even if the noise in the input makes it return a little bit. We can make a comparator with hysteresis using positive feedback in an op-amp. The following diagrams show the circuit. The interesting part here is the voltage divider connected at the output. The voltage divider is used to provide a voltage to the non-inverting terminal. We know that the output of the comparator can take two values, VCC plus and minus VCC. This will make the voltage at the non-inverting input jump between two values that are given by the following formulas. These two values are the voltage thresholds. As you can see, we can define what the thresholds will be by designing the voltage divider at the output. It is important to notice that the thresholds depend on the actual output voltage that the op-amp can provide. In the following simulation, we can see how this comparator behaves. The threshold voltage are calculated to be 1.09 volts and minus 0.9 volts. In the plot, we can see the noisy input. As soon as it crosses the threshold, the output comparator changes and the threshold changes as well. The threshold, which is the voltage at the non-inverting input pin, is displayed in green. As we can see, there are no bursts of pulses at the output. It is important to notice that the output of the comparator is inverted. When the input signal is positive, the output is negative, and vice versa. This is an inverting comparator. What if we want the output of the comparator to not be inverted? To do that, we can change the circuit as follows. In the diagram, we can see that the input signal is now connected to the bottom of the voltage divider. The inverting input is connected to ground. In the simulation, we can see that the circuit behaves correctly. However, the formulas to get the thresholds are different. If you want to get the formulas by yourself, you need to calculate the voltage at which the non-inverting pin crosses 0 volts. In this lesson, we learn about 3 types of circuits that can be used as comparators. First, we have the basic comparator. This circuit takes advantage of the high gain of the op-amp to produce an output voltage as soon as one of the input voltages exceeds the other. Then we explored comparators with hysteresis. These use positive feedback to establish threshold voltages, creating a safe zone that prevents the comparator from making quick changes due to noise. As a last note, when comparison operations are needed, it is often better to use specialized integrated circuits designed specifically for comparisons.